Hello, this is Animita Roy and this is my presentation on the topic Performance Evaluation of Cooperative Spectrum Sensing in Cognitive Radio Network for Additive Wide Gaussian Noise Channel and Rayleigh Fading Channel. The main objectives of doing this project has been stated in this slide. First, we have quantitatively tried to find out for a fixed gain and a fixed number of secondary users the average error probability that for different types of channels. Secondly, the performance of cognitive radio system has been evaluated mainly based on the two important factors, probability of detection and power efficiency. Thirdly, an optimal sensing time has been determined. Different rules of fusion at the receiver have been discussed. A comparison has been done between the Rayleigh fading channel and the additive wide Gaussian noise channel, and an alternative method to improve the performance of the system has been discussed. In cognitive radio system, the secondary users can use the frequency bands when the primary users are not present. Therefore, the secondary users need to sense the channel periodically. When the primary users are detected, the secondary users have to stop using that channel. This makes the probability of detection important for the cognitive radio system. However, detection is compromised when a secondary user experiences fading. That was the main concept behind this project, and we have tried to find out in a cooperative spectrum sensing system when the system experiences fading, what happens to all the system parameters. So what is cooperative spectrum sensing? When instead of only one secondary user sensing the channel, two or more secondary users sense the channel coordinately and share the information between each other. This method is very useful because the probability of error reduces in this case, and also it increases the reliability of the system and reduces the hardware requirements. The major problem in cooperative spectrum sensing are now discussed. The main idea of cooperative sensing is to enhance the sensing performance by exploiting the spatial diversity in spatially located cognitive radio users. By cooperation, the cognitive radio users can share their sensing information for making a combined decision more accurate than the individual decision. The performance improvement due to spatial diversity is called cooperative gain. The cooperative gain can also be viewed from the perspective of sensing hardware. So this diagram shows all the losses that can incur during cooperative sensing, where there can be path loss due to distance, and also there are loss due to multipath fading and shadowing. This reduces the signal to noise ratio of the primary signal from the primary user. Since the signal to noise ratio is low, it becomes difficult for the receiver to detect the weak signals. Even if we impose very strict sensitivity requirement, then the implementation and the hardware cost increases. More importantly, the detection performance cannot be improved by increasing the sensitivity when the SNR of the primary user signal is below a certain value known as the SNR wall. These are the problems incurred during cooperative spectrum sensing. So this is our cooperative spectrum sensing model. In this paper, we have considered a cognitive radio network with k cooperative secondary users. Spectrum sensing is performed periodically every n samples, which is total number of samples for each secondary user. For the ith user, the secondary for the ith secondary user, it is modeled as a binary hypothesis test to determine the absence or the presence of the primary user. This has been shown in the equations in the slide. H0 represent the hypothesis when the primary user is absent, and H1 represents the hypothesis when the primary user is present. Here in the equation, YIN is the received signal from the secondary user. SN represents the primary user signal sample which are independent. Energy detection in non-fading channel, which is basically additive wide Gaussian noise channel. These are the equations for probability of false alarm, which means that when which defines the probability of the sensing algorithm falsely declaring the presence of primary signal under the hypothesis H0. PD is the probability of detection, which defines the probability of the sensing algorithm correctly detecting the presence of primary signal under the hypothesis H1. Energy detection in fading channel, which is basically Rayleigh fading channel. The probability of false alarm in a Rayleigh fading channel remains the same since it is considered for the case of no signal transmission, and as such it is independent of SNR. When the channel is varying due to fading effects, the equations for a non-fading channel are represented by the instantaneous SNR of the system. Nakagami channel is a special type of channel that was introduced in the early 1940s to characterize rapid fading in long distance high frequency channel. The Nakagami M distribution is used in communication systems to characterize the statistics of signal transmitted through multipath fading channels. The Nakagami distribution is often used for the following reasons. First, the Nakagami distribution can model fading conditions that are either more or less severe than Rayleigh fading. Here we have defined a relationship between the rise factor K and Nakagami shape factor N. When M is 1, the Nakagami distribution becomes a Rayleigh distribution. When M is equal to half, it becomes a one-sided Gaussian distribution, and when M is equal to infinity, the distribution becomes an impulse, that is, no fading occurs. Now we will discuss spectrum sensing based on decision fusion. In cooperative spectrum sensing, all secondary users identify the availability of the primary user independently. Each secondary user makes a binary decision based on its local spectrum sensing and then forwards one bit of the decision to the common receiver. The decision can either be 0 or 1. That means if it's 0, the secondary user concludes that the primary user is not present. If the decision is 1, then the secondary user concludes that a primary user is present. Once the decision is made by each secondary user, there are different rules available for making the final decision on the presence of a primary user. At the common receiver, all one bit decisions are fused together. That is the reason why it is known as decision fusion. Now the different rules for decision fusion are discussed. First is the logic OR rule. The common receiver infers the presence of a primary user signal when there exists at least one secondary user that has the local decision H1, meaning that if one secondary user has inferred that a primary user is present, then the decision at the common receiver will be that a primary user is transmitting, so all the secondary users should stop their transmission. The mathematical equation of this rule has been shown in the slide. Logic and rule. The common receiver infers the presence of a primary user signal if all decisions say that there is a primary user. This is basically how an AND gate works. The mathematical equations are shown in the slide. That is, for a hypothesis to be H1, that is, to infer that maybe a primary user is present in the system, all the secondary users have to conclude the hypothesis H1, that is, all of them have to have 1 for the presence of a primary user. Majority rule. This decision rule is based on majority of the individual decisions of secondary users. If half or more of the decisions say that there is a primary user signal, the final decision declares that there is a primary user. The probability of detection and probability of false alarm are beyond the scope of study. It can be seen that OR rule is very conservative for secondary users to access the license band of the primary user. As such, the chance of causing interference to the primary user is minimized. This will be shown later. Sensing power efficiency and probability of detection trade-off. The main parameters that are used to evaluate the system performance are probability of detection, probability of false alarm, power efficiency, number of secondary users, number of samples during the sensing period. In the proposed solution, the sensing time has been divided into two parts. In the first phase, we use only a value of samples less than the total number of samples to check the channel states. This we call the checkpoint of the sensing time. Then a certain number of users less than the total number of users which are in the deeply faded channels are discarded. Thus, after the checkpoint, fewer number of secondary users are remaining, as well as the number of samples are reduced. So, the total power consumed by the system is lessened. So, from there, we can derive the optimum sensing time. So, we can derive a target function to determine the optimal sensing time, then jointly maximizes the probability of detection and minimizes the power consumption under given parameters. As there is a trade-off between the probability of detection and power efficiency, we define the target function t as the mathematical expression shown in the slide. Here, alpha is a constant which is varying between 0 to 1. If alpha tends to 0, the detection of probability is regarded as a more important factor. If beta tends to 1, then the power efficiency is regarded as a more important in the detection than detection probability. Another alternate method to improve the system performance can be discussed. Here, instead of randomly discarding the secondary users, we divide the users on the basis of the signal strength. The secondary users with weak signal strength, that is the signal which is below a predefined threshold, are discarded, and secondary users with high signal strength continue to track the activity of the primary user. Performance evaluation of observational fusion channels. Here, 3 cases have been discussed. Case 1 for observation channel fusion channel having AWGN and Rayleigh fading have a high SNR. So, this has the best performance. In case 2, with Rayleigh fading as observation channel in AWGN as fusion channel, it has low to moderate SNR. So it has a low average error probability among all the 3 scenarios. This is our simulation and results. This graph shows the cooperative sensing using the AND rule discussed previously for additive white Gaussian noise. This shows the graph of power efficiency versus the number of samples for different values of K. We can see that as the number of samples increase, the power efficiency of the system is also increased. This is a graph showing the optimal sensing time variation with target function and a number of samples. Using mathematical functions, we have found the value of the target function to be 0.5 to be optimal for the system to work perfectly. Future work. The future work that we can do from this work is do cluster-based cooperative spectrum sensing. The cluster-based leech-C protocol is implemented where secondary users are grouped together to form clusters. The user with the highest SNR is chosen as the cluster head. The main advantage of this kind of system is that instead of all the secondary users participating and transmitting their decision to the common receiver, only the cluster heads forward their decision to the common receiver. This leads to a reduction in the number of signals that the receiver has to receive and also simplifies the hardware implementation and cost. This also minimizes the total energy required by the system. Thank you. I would like to thank Dr. Wu for giving me the opportunity to work on this project, which helped me learn a lot about cooperative spectrum sensing in cognitive radio.